Hey, welcome to the ZP Developer Zone webinar. So we do this webinar every Thursday. We try to do it every Thursday at 8 a.m. London time. And it's really just answering technical questions that have come in from the week. We tend to do sort of commercial questions, really can part of projects, but questions that kind of come in from universities and students or collaborators, and we can quickly answer them. We do try to do that through these webinars. Of course, we do our ZP Academy. So if you're interested in this, getting some free information on the science of electrochemical biosensors, then there's 2 free courses on the ZP Academy. Of course, we do this webinar every Thursday at 8 a.m. London time. At least we do attempt. We do collaborations. These collaborations are generally with universities in the UK and Norway because of the funding options there. We do offer jobs. We just brought on a new person in Norway at the moment. We do have our ZP Developer Zone as a dedicated website, and we do workshops. I think workshops are really important because actually some of the technical questions that have come in this week, they actually get covered in quite in depth at our workshops. So if you see a link appear today, that means we will also have it underneath the video as well if you're watching this on YouTube. So we do have some workshops in June in Coventry and Horton, so one in Norway, one in the UK. Coventry's not too far from London, so just to give you some context. On train, it's less than an hour. So question number 1 was really about CFU, colony forming unit counting. So CFUs per mil, how do we measure them? I'll answer that. Another question on urinalysis. This question, several of the questions actually kind of are related to this in some way, but we'll answer some questions about urinalysis, and we'll also answer some questions about lactic acid. Depending on your perspective, lactic acid is either a sort of biomarker sometimes for athletic workout, or sometimes a biomarker for sepsis, sometimes a biomarker for bacteria, and I'll discuss that. We will discuss screen printed electrodes. Somebody sent us some images with when the electrodes have kind of tarnished, and I think it's really linked to storage conditions, and we will address that today as well. The same group has also sent in some data for potentiostat, and I will address that as well. I have a sort of another question layered in here, which is NADH. I'll just do a quick discussion on NADH sensors. And then actually also I've got some data from question 5, 6. How do I put this? Sorry, questions 4, 5, and 7 are the same team, testing SPE with blood, which is then kind of interesting because testing blood is also linked to urinalysis. So lots of these questions, different perspectives, but actually interesting overlaps. Question number 8 was really linked to urinalysis as well. Somebody was just asking about the speed of response of a sensor. Most of our sensors are responding in the seconds time frame. I say most of them. I'd almost extend to say all of them. Also I want to sort of talk about building business models case for biosensor applications. So I can see some of the questioners, you can see from their profiles, they're not so much in the biosensor development interest. They're actually more interested in building business cases for biosensors, and that's something that we really discuss in our workshops as well. So question number 1 was about sensors for CFU per mil. So CFU stands for colony forming units, and then you put per mil is quite standard, but it just, per volume. So at ZP, for example, we do a lot of like E. coli and bacterial type sensing. This is one of our sensors. We did this a few years ago where we had a sensor in a solution, and it's cloudy because there's some bacteria in there, and then we let that bacteria sort of grow over time. So we've been working on technologies around bacterial detection for really quite a long time now. The traditional way of doing CFU counting, colony forming unit counting, is you would take a Petri dish. This also plays in a bit with urinalysis as well, by the way. You would take a Petri dish. You would have what they would call a gel on there, an agar gel. Gel is basically this food. and you would actually put your sample around the bottom of this Petri dish, and then after 1 to 3 days, you would look at it, physically look at it, and you would see these kind of spots, and these spots are basically what you assume is some bacteria was there, and it's grown up to be large enough that you can now count it. And literally, people just count it by eye. And so, in this little simple example, you would say, I see three colonies. I know what my volume is, so I say it's 3 CFUs, 3 colony forming units per mil. So that's what the question is how do we make a CFU per mil sensor? Now, if you've got like a sort of a tank, and in that tank you have some water, you can put sensors in there. But of course, in a Petri dish, you actually have quite a large surface area and a very small volume. So you're quite efficient at counting and collecting the bacteria in that Petri dish. When you've got like a tank and a sensor in it, you've actually got a massive volume and a small sensor. So you could have bacteria in that tank, but actually it's away from the sensor. So it's like looking for a needle in a haystack. I will address that in a minute as well, by the way. I do want to say that. But I also want to say that people have been interested in making sort of bacteria and CFU sensors for years, but it's a tough challenge. One way that they try to address this in academia is they will actually try to take an electrochemical sensor. By the way, we have done this kind of work ourselves, where we'll put an antibody on the surface, and here you're essentially putting molecular biology. In fact, no, I'd call it immunobiology or immunochemistry on the surface, and this surface becomes very specific, so the bacteria binds to it. Now, this is something that we do a lot of that kind of work at ZP. Whoops a daisy. And then you would put that sensor in the sample. In the water tank. Quick thing is, those types of sensors work great in clinical settings, but they're not robust enough to be in a municipal water tank or an industrial water tank. They're just not. The way these kind of immunosensors would work is you would put a sample on there, get result, throw the sensor away. There's no need for long-term survivability. Another way of detecting CFU is to actually use what we call surrogates. So, for example, in some water systems, some bacteria, a lot of bacteria are associated with biofilms. And so these biofilms, if they were to impact our electrodes, we'd actually be able to detect it. So I think sometimes it's you don't have to target the bacteria directly. You can target biomarkers or surrogates for that bacteria. So finding a single bacteria is quite tough. Bacteria that form films, films are larger objects. Essentially, there's more signal associated with them. That's a sort of easier target. I do want to say again, on the world of biomarkers, I want to make... sorry, I just lost connection for a second there. I just want to make the comment that purines are a biomarker also for bacteria, and also it does play a role in urinary tract infection. And as that said, we have these products for that as well. The reason I was saying all this is because you sometimes don't, in some applications, you don't really want to detect the bacteria directly, because the sort of science to do that is actually quite tough, and you're better off trying to go after one of the how do I put it? Go off after one of these biomarkers instead. So I will go on a bit further. I do want to address that point earlier on about when you're trying to detect bacteria or CFUs in a tank. If the bacteria is on one side of the tank and the sensor on the other side of the tank, you can't be kind of certain that the bacteria is actually getting to the sensor. So we end up building things like recirculating systems, where we kind of we're trying to make sure that a certain amount of the bacteria or the sample is getting to the sensor. So what do I mean by that? What I mean by that is this is a rig that we've built where we have like a sample reservoir here, or this could be a much bigger tank. We have pumps, and the pumps are essentially to sort of obviously raise liquid and move liquid. We have pressure valves, and we can either go to waste or we can recirculate. So we're quite good at doing this kind of work, and actually in the heart of it there's a sensor. So what I'm saying here is, if you're trying to monitor water systems, then the sensors really only clearly, the team asking about this is an engineering team. The sensors really only part of it, if I could put it that way. And we'd also have to be involved in the mechanical part of bringing the sensor to the sample. So there's the sensor in the middle of that. Just want to check something online. Right, so and with that system as well, we also have the capability of bringing that data to the cloud, and we have the electronics in place as well. So I think with this kind of, if I say stuff, then I just want to with this kind of stuff, we have the electronics, we have the electrodes, we obviously have kind of cloud communication. The bit that I'm concerned about is the actual method to count CFUs per mil. There is not a CFU per mil sensor out there. There are sensors that will detect the presence of or are correlated with CFU per mil, but they don't actually exist. So it's a sort of more of an engineering challenge than people would otherwise like to think. Question number 2 is about urinalysis. We seem to have a spate of people very interested in urinalysis at the moment. I have 2 questions. I've previously answered on this, but I must have sort of indicated that we had more sensors and more capability in urinalysis than is necessary on the website, so I will address that. Second question here is about cortisol. We do have a cortisol sensor. It's a very serious sensor, and we are using it with well-funded companies, but it's not something that we're able to really discuss unless somebody's really got the budget to have this to be engaging with ZP. So I'm not going to discuss cortisol sensing. But in terms of urinalysis, I did a quick search to just see. And urinalysis, actually, I think this list is a little short, but people are obviously interested in pH. We do have pH sensors. People are interested in protein. Protein is something that we don't have on the web store, but we are capable of detecting proteins. I mean, how do I make that statement? Because most enzymes and most enzymes and sort of many markers for diseases are actually proteins. Sugars is something that people do urinalysis on. Obviously, we have our glucose sensors and fructose sensors actually. And bilirubin is something that people try to detect in urine. There's bilirubin, there's hemoglobin, and there's blood as well. These are all things that people detect when they're doing urinalysis, and these are all addressable by ZP's technologies. People are very interested in infections. That's why they're interested in leukocyte esterase and nitrites. ZP does have experience in both of these things. We don't have it on the web store. But when you're looking for urinary tract infections, UTIs, I sort of addressed it just a minute ago. There's actually ATP and purines as well are also indicators of the bacterial presence for UTIs. I think when I was talking earlier on as well, in a previous video, I sort of said, oh yeah, we got other sensors. I was actually thinking about urea at the time, but I kind of think now, well, it's obvious that urea is going to be in urine, so I don't think there's much clinical utility in determining that there's urea in urine. It's a bit obvious, but we do have that sensor as well. I was just making this statement that we could detect blood in urine, and we actually have quite a nice technology for this, sort of based on our typical thing that ZP does. We make low-cost biosensors, or at least on a low-cost sort of platform. And in this kind of video here, we have a little sample sitting on one of our sensors. I know the hand keeps getting in the way, but there's a little sensor there with a little sample on it. That's the nice thing about electrochemistry. You don't need much sample in order to do this kind of work. and then in a minute what he does is, or they do rather, is just bring in a little drop of iron in this case, but iron is also a biomarker for hemoglobin, bilirubin and red blood cells, and immediately the screen will change to iron detected, iron not detected, and then once you've done that, iron detected. So we do have some pretty neat technologies that are kind of very kind of smartphone enabled, cloud enabled, able to detect markers for things like blood, bilirubin and hemoglobin in samples like urine. And I'll sort of thrust on a little bit further. Any kind of links, I've hopefully already put them underneath the video, so hopefully that will help. Question number 3 is about lactic acid. In one of our videos, one of the engineers said, sort of made a comment that, oh, well, you didn't test with sodium lactate, you actually test with lactic acid. The reason we do that actually is because we were realizing that we were making a sensor for L-lactic and people were actually testing with D-lactic. We now make sensors for both, by the way, L and D. If you really want to understand whether you need an L or a D sensor and you can't figure it out from the literature, then engage ZP in a consultancy and we'll help you figure out which one you actually need. But we do have a lactate sensor, and there is a subtlety to lactic acids, that it has an L and a D form. These are sort of chiral enantiomers of one another. It's the kind of stuff that you do learn in high school chemistry, and then it's definitely in your first year of a chemistry degree. This is the kind of stuff that we are learning, so it's quite clear to us, but it's not always clear to others that molecules can have a left hand side and a right hand side. Screen printed electrodes. So somebody was kind enough to buy some screen printed electrodes from us. After a few months, they've tarnished. Now we've seen this before, and I've seen this in climates like Southeast Asia, where it's really reacting with the atmosphere. So things that accelerate this kind of corrosion is light, humidity and temperature. The thing is, it doesn't actually affect these sensors too badly, but we do often store our electrodes. I call them sensors. They're really at this stage electrodes. We do store them in a sort of dark, dry and cool place. I think it's a bit extreme to put them in the fridge, but if the fridges are dry, because generally the air is so cool that actually all the condensation is out of them. The door is shut, so they tend to be dark. So they and they're a fridge, so they're cool, so they actually meet this criteria. So you can, at an extreme, keep things in the fridge. I don't think you need to, but when I do see cases like this, it's either been exposed to light, humidity, temperature, or a combination of two or more of these parameters. I do highlight these electrodes. These electrodes are sort of, we sell 250 of these for, 300 of these for €250, so they're really less than €1 each. So it's not the end of the world if this happens to you. It's a shame. Just store them properly. But it wasn't the biggest financial hit that somebody would ever have. We do obviously do a lot of testing on these, and we do understand, we've characterized them quite a lot. So it's kind of interesting to see, because they sent me some data that said, well, this is the CV within a month. So when we first got it, this was the CV, and they've shown me the peak positions here, 40 millivolts, 270 millivolts, and then they've tested 4 months later when they're, let's say, they've discolored, and then they're highlighting that actually the peak-to-peak separations increased quite considerably. But what's interesting is actually when they tested within a month, they were testing at like 2 milligrams per mil, and now they were testing at 13.76 milligrams per mil. So it's not a one-for-one comparison. If you want to make a one-for-one comparison, you have to use the same concentration. So this peak separation, you can assign it. You could say, oh, well, I look at that image, it's assigned to this discoloration. You could also assign it to the fact that you're testing at different concentrations. If you look at a lot of data in the literature, especially on cyclic voltammetry, you'll notice that their signal increases with concentration or scan rate. That's a typical experiment. But what you don't notice sometimes is actually the peaks separate. So as the signal comes up, the peaks separate. This is called IR drop. And it's not a disaster. But so what I'm saying to you is that actually you're assigning this peak separation to this corrosion, you could also assign this to actually the fact that you're doing this experiment at 2 different concentrations. There's an order of magnitude difference here, and actually you've got more IR drop at these high concentrations. I'll give you an example. So before we ship, we often test our electrodes at something like 5 millimolar ferricyanide. This one is done at 10, 20, 50, and 100 millivolts. As we increase the scan rate, we're essentially increasing the current, and you notice that our peak is actually shifting, and it does that on the oxidation, and it also does that on the reduction. So what I'm saying is, you think that your peak shifting is due to that discoloration. It could be, but I would also argue that it was actually you're also using different concentrations, and you know, as we increase in this case scan rate, you see us shifting. In your case, you've changed concentration and you're shifting. So I think it's I'm just sort of illustrating you here. As the current goes up, the peaks tend to shift, and as the current in the reduction also increases in magnitude, the peak shifts. So you end up with these 2 peaks sort of coming away from one another. They've also sent me some data on testing a potentiostat. So they've taken a potentiostat and they've tested it with 100 kilo ohm resistance, and they've essentially just sort of scanned the voltage, and you get a straight line because it's just testing a resistor. So this is basically Ohm's law. Voltage is equal to current times resistance. Now obviously I can just eyeball this and look at the current, look at the voltage, and I should be able to therefore calculate using Ohm's law the resistance. When I do that, I end up with a resistance of 10 mega ohms. I have a sneaky suspicion that this is not a 100 kilo ohm resistor. I think this is a 10 mega ohm resistor. If you want to really find out, make a video where you show, I take a voltmeter like this, I test that resistor, and this voltmeter will report, it should report 100 kilo ohms. I suspicion that the voltmeter will say 10 mega ohms, and then take the same resistor and test it on the potentiostat, because that's a way of confirming that the resistor is what it is. Before you sort of point fingers at the potentiostat, independently confirm that the resistor is what you say it is, because it's more likely to be the resistor here rather than the potentiostat. Is my comment. And I also think with the questions that have come in, I would strongly suggest that this team comes to one of our workshops. We do have one in Norway on the about the 20th of June. Do come to it, because all these questions really will get covered there, and I think it will really help the project as well. And we do have a question about NADH. Somebody has some NADH sensors. Do they use chronoamperometry? Do they use cyclovoltammetry? How sensitive is this ZP NADH sensor? So this is, and do we have any information about how it works? So I will address this. First of all, there's a link here. This link is where I found this data. This is one of our sensors. And when I read here, this is being tested at 200, 400, 600, and 800. So 200 micromolar, 400 micromolar, 600 micromolar, 800 micromolar. So their question is, can we detect, for example, the first part of the question is, can we detect 100? Well, 100 is about here. So 100 looks very detectable. 10 is probably okay, because I can still see the noise on this data is very small. So 10 is sort of here. 1 probably takes some optimization and some work. So I'm not sure about 1. 10, yeah, just about. And 100, yeah, clearly I think we can detect 100. The way we did this experiment, I should say that these people have what's called an Anapot EIS. This is a perfect instrument for this. And we used chronoamperometry at, this is a dash, it's not minus, at 0.1 volts versus reference. So we did chronoamperometry. We probably had a save rate of something like 1 data point per second, and we were applying a voltage of 0.1 volts per second. The other part of their question was, how does it work, and cyclovoltammetry. So what we've done is we've taken our electrode, we've basically functionalized it with a surface of oxygen atoms, and those oxygen atoms are quite happily sitting as oxygen. Now, what NADH is doing is it's actually converting those oxygens to alcohols, and the electrochemistry then turns the alcohol back to oxygen. So that's the source of the signal. So we have a surface of oxygen atoms. NADH comes in, makes those oxygens alcohols, and then the applied potential reoxidizes the surface, and that's the source of our signal. If you were to do this experiment by cyclovoltammetry, you could just do a CV in the cyclovoltammetry in the absence of NADH, and you would get a CV. This is one for ferricyanide, so this is not quite what you get. This was an animation that I could find quite quickly. As you add in NADH, the oxidation peaks go up and the reduction peaks essentially go down. Now, the reason this happens is because the surface is oxygen. The NADH turns it into alcohols, so we have plenty of alcohol now to oxidize. We get lots of oxidation signal. When you try to do the reduction, the surface is already being reduced by the NADH, so we got less material to reduce. So as the NADH goes up, you find that the oxidation part of a cyclovoltammetry goes up and the reduction part goes down. Cyclovoltammetry is not particularly sensitive technique. We use cyclovoltammetry as a quality control tool and also as a fabrication tool if we're trying to do what's called electrochemical polymerization, for example. So I don't recommend CV necessarily. There are lots of voltammetric techniques out there that if I was trying to work on that 1 micromolar NADH thing, I'd probably start to try use techniques like square wave voltammetry and differential pulse voltammetry. Now, we do discuss this in quite a lot of detail at our workshops. I would really suggest, if you want a good start on this program, I would actually say come to one of our workshops again. There's one on the 20th in Norway. We do try to hold them every month. We're coming up to the summer soonish, so we do try to hold them every month. So reach out to me about a workshop, or I've also put links here as well. This question has really come from the similar team earlier on that had the corrosion issue with electrodes, or the discoloration, if I can call it that. It's not absolutely clear it's corrosion, but they're definitely discolored. And they also had a sort of, I think the resistor value that on that potentiostat that you were testing, that resistor with was wrong. But this does play back into this whole idea of testing for blood in samples. And here what they've done is they've taken a sensor or an electrode and they've added increasing amounts of blood, and the signal goes up accordingly. I mean, for me, that makes perfect sense. We do a lot of this kind of detection of blood. The blood is probably undergoing lysis. The hemoglobin is probably spilling out, and you're essentially detecting the hemoglobin directly. So basically, all I can say is it looks like it's working. They did send me some other data, but it wasn't annotated, and it just wasn't clear what we were looking at. Question number 8, and I'm sorry for going on because I think we're like 28 minutes into this or something like that, 29 minutes, so I'll try to go a bit quicker. Speed of response, this was linked to urinalysis. If somebody was doing multiple, you wouldn't, they were asking really what's the speed of response, and the speed of response is pretty fast. This is 200 seconds here, so signal is just jumping up. It's almost like there's an old toy called an Etch-a-Sketch where you kind of twiddle knobs and the line moves around. You can see how quick these are to respond. So most of our sensors are actually really fast to respond. I say most of the things that are on the web, if we've got a biosensor on the website, you will find that we always have raw data there, so you can always eyeball it as well. Multiple analytes is something that we're pretty good at. This is a cartridge that can carry 6 sensors at a time. This is the kind of form factor that we end up delivering. If somebody wants to do multiple analytes, because they're doing some sort of urinalysis type product, then we do have that kind of tech in-house, and I think I've put a link to it, so yeah, you can find some links to that. Question number 9. This is really some of these questions that are coming in, especially on urinalysis. We've had a couple of people asking about this recently. It's really something that we cover quite a lot in workshops, is really sort of strategy about this and the commercialization of this. So I would encourage people to come to our workshops, because the science of technology, as the questioners will know, and many of you will understand, it's really a small fraction of the whole problem. The big problem is actually the business model. So we do talk about business models and sort of strategies. Do you have a sort of business to business strategy? Do you have a business to consumer strategy, which is the hardest strategy and needs one of the most well funded? Business to healthcare provider, this is a really hard strategy, especially if you try to do it in the UK with the NHS. Business with partners, that's kind of business to business, but business, it's really just saying, that actually, yeah, if you can find somebody with an incumbent in a market and you can feed your technology into them, obviously that's the best way of scaling. But we do discuss this in our workshops. So even if your questions sound like of a technical nature, I really think your questions are actually of a commercial nature, and that gets covered in our workshops as well. And we will discuss things like Vivo. This is a urinalysis system where they really went business to consumer. They also tried to do business to business by working with gyms, let's say, but it's business to business, business to gyms is business to consumer, business to gyms is their model. And we can discuss things like that in the workshops. So CFU per mil sounds like a really simple thing, but actually it's not just the sensor. It's really sizing or really thinking through how to get enough sample to that sensor that what you're sensing is actually meaningful with regards to the total volume. Do you try and detect the bacteria directly, or do you actually try to detect the bacteria indirectly? And this really needs some consulting time to work through all of that. Urinalysis, I at least saw that there was pH and glucose was in urinalysis. We obviously have pH and glucose sensors. And I've also, through this week as well, been touching on blood quite a lot in urine as well. And that really falls under urinalysis as well. Lactic acids simply tell us whether you need D-lactate or L-lactate, and if you're not sure, consult with us. Screen printed electrodes, that discoloration is probably linked to storage. I've only really seen that a few times in India, where they do have a lot of sunlight and a lot of humidity and a lot of temperature. And I would also say that if there's too many variables in that data set to say it was actually the corrosion, biggest variable being concentration. You need to test at the same concentration. Testing that potentiostat, I really think that resistor is not right. Test the resistor on that, make a video of you doing that, test the same resistor on the potentiostat, get the same line, and then we can dig into that a little bit more. NADH, chronoamperometry, 0.1 volts, 100 micromolar looks very doable. 10, probably even that is doable. 1, you're probably on the edge of detection. It can happen, by the way. 1 micromolar is not a low concentration in the world of biosensing. It's not. I mean, it's actually fairly high. It's just, it's not, looking at the raw data, it's not optimized to do that 1 micromolar. Testing SPE with blood, nice data. Your signal increased with blood. I'm not super surprised. I've put a video in ourselves where we were actually being able to detect things like iron-bearing molecules in samples. So your signal makes sense to me. Speed of response, most of our sensors will respond on the second type timescale. So it's not like you're waiting 30 minutes or something. I suppose that's it. The thing is, see, with urinalysis sticks, I understand why they ask the question now. Their color change sticks can take a while to develop the color. Now I understand the question, yeah. But of course, yeah, our electrochemical sensors are responding much quicker. And then this is really linked to that. Building a business model, business case for biosensor applications. That's something that we do cover in our workshops. I'm sorry if the video came on and off a few times. For some reason, I was getting a few dropouts today. But thank you for your attention. There's a vlog on Sundays at 8 a.m. London time. That's just a roundup from news from ZP for the week. But if you have any technical questions, then this will repeat next Thursday at 8 a.m. London time on the 15th of June. Okay, thanks very much.